time to begin the last colloquium of this semester. Today's speaker is Professor Youngjoon from KAIST. Let me briefly introduce his biography. So he received his PhD back in 2015 at Indiana University, and he moved to University of Illinois Chicago, and he worked there as a research assistant professor, and then he moved to San Diego State University and worked as tenured assistant professor, and he moved back to Korea, worked at Youngjoon University, and now he's associate professor at KAIST. So it's a great pleasure to have him as our colloquium speaker. He's going to talk about theory-guided machine learning for partial differential equations. Please join me in welcoming Professor Hong.
Okay, thanks for the invitation. It's my honor to speak post a colloquium here. So actually, my title is like theory guided machine learning for partial differential equation, but I just slightly oops, I'm sorry, changed my subject as a machine learning approach in scientific computing application, if you're fine. Okay, so let's get started. So I think most of you know all about this kind of the great success in AI and machine learning. And on the left-hand side, this kind of video is like Sora from OpenAI. It's very shocked at the beginning because if you like the prompt here, like the movie trailer featuring the adventures of the 30-year-old spaceman wearing a Red Bull, eating motorcycle helmet, blah, 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 then the OpenAI Sora generates this kind of video. So Hollywood, they are kind of in trouble right now. And also in South Korean movie theater, this kind of thing is going to be shocked here. And well, this is multimodal, the multimodal architecture, and that's very, it's very, very difficult job, in fact. But right now, it's possible. So this is a very, very advanced one in the moment, for the moment, and on the right-hand side. So this is like the for Korean. So this is like the robot advisor for this kind of the trading of the stocks of option markets, and then this kind of thing. Actually, in fact, our team developed this kind of the trading, the AI, this kind of the robot advisor thing. But they sell it to the marriage, the marriage one, but they didn't give me any incentive for this. So I just make use of this title and article for my lecture. Anyhow, this is kind of the great success, and also it is possible this kind of the high resolution thing. Like if you watch the CSI movie and they have some kind of trailer and this kind of some suspected, and they have some kind of detective trying to find some kind of the surveillance camera, and the camera is like low resolution, and they just making larger and larger and larger and go to the high resolution. Actually, that was fake at the moment, but right now it's possible because that kind of high resolution is possible by using the deep generative model and this kind of technique. I will come back to this kind of thing. Where can we use this kind of high resolution in science? Okay, so yeah, I just talk about a little bit of a strange story. It's not mathematics, but I'm a mathematician. So how can we handle this kind of thing into math world? So that's our major question for that. So let me talk about brief on my background. Actually, I'm a applied mathematician. I'm working at this kind of the numerical PDE for my PhD. So I actually work on this kind of singular perturbation and boundary layer for the given partial differential equation. So that is one of the big problem in numerics and also in theoretical PDE problem. So you can think about this kind of the wing, and there is just some kind of flow, and you can see this kind of a very thin layer nearby this kind of the wing, and we call this a boundary layer. And you can expect very sharp transition nearby the boundary layer. And numerically, it's really hard to capture it because of very thin layer and sharp transition. That's not going to happen by using the classical numerical method. So I make use of some of the numerical technique, like the theory-based numerical technique, and then resolve this kind of issue. That was one of the PhD problem. And also, I work on this kind of the computational material science. So it's basically we are going to solve the Maxwell equation, time harmonic Maxwell equation by using numerical method. So we have a many layer, and we are going to simulate it. So this is like the actual situation. Like we have a nanoscale, we have a stack of the materials, and we can simulate by using the Helmholtz equation and the Maxwell equation and some numerical technique, and we can find numerical solution. And then we can find this material is good or bad. So this is quite interesting because the physical simulation is quite expensive. And once you build this kind of nanomaterial, you can change the material. If you want to change material, you have to throw it away. Then you can build new material, nanostructure. So that's expensive. But numerical simulation, it's almost free. So, that's quite popular. Like computational material science is quite popular subject in these days. And also another thing is like geophysics. So this is sort of the implicit, sort of the Euler type of equation. We call this one is implicit primitive equations. So actually this equation used for the numerical weather prediction. So for instance, if you have this kind of mountain and flow moving from left to the right, then you have condensation and raindrops and hot and dry air going down here. And then if you imagine this one is like a rocky mountain, and then you can think about the hot and dry air going down, that could be like a wildfire and some of the issue. And you have a lot of rain here, then it's flood and another issue like the left hand side of the mountain. So that kind of thing is very important issue for numerical weather prediction. So actually that kind of numerical prediction can be done with this kind of the partial differential equation. And we call this one is a numerical weather prediction problem. And that was my PhD thesis. And recently my interest is in like this kind of the neural networks and something like some weird thing. It looks not very close to mathematics, but I'm going to explain why this is close to mathematical problems. So on the left-hand side, this is like the deep generative model, the differential model by using the graph neural networks. And this one is like some architecture by using the ODE, the neural ODE test. And this is like the PD solving neural network architecture. I'm going to explain this kind of thing for today. So this is some outline of my talks. So first one is mathematics of machine learning, and second one is machine learning for science, and third one is machine learning, mathematics and machine learning working together. So I'm going to mostly focus on the third part, but on first and second part, I'm going to briefly talk about it. So I know all of you knew this kind of the figure, like this is like the neural networks and this diagram. And this diagram actually, in fact, this is like this kind of the composition of the function. So sigmoid function, hyperbolic tangent, that could be activation function. So it's like, in fact, neural network is very close to the functional approximation. So that's what we did in mathematics long time ago. But suddenly they introduced very deep layer, and the function becomes very complicated. So we having trouble because we got trouble because the analyze of this kind of the deep neural network is very complicated. But this kind of the architecture is very close to our function approximation. And well, we can say mathematics for machine learning, so we can understand machine learning by using mathematics. So that's kind of catchphrase. We are mathematicians, we can analyze machine learning and neural network by using mathematics. But can we really do this? That is actually a little far-fetched for the moment, but we are gradually building our idea and our construction. So eventually we are get to the analyzing machine learning in the future. That's our eternal goal for that. So of course we need many of the mathematical technique to think about the machine learning, other kind of the deep learning architectures. So one of the tangible goal is error estimates. So I said machine learning is like the functional approximation. So we can do the error estimates. So normally we can say neural network has 3 different errors: approximation error, optimization error, and the generalization error. And these 3 errors we can analyze one by one, but each of them has their own difficulties. So they are not easy to analyze. Of course, we have a very shallow neural networks. We can do some, special space to analyze it. If we have some wide neural network and depth neural network, we can do that. But like the general theory, we don't know where about this kind of general theory. And optimization error, that's kind of widely open for the moment. So these are quite interesting. So there are many things that have been done in this direction. But today I'm going to talk about a little bit different direction, like the generative model. So how can we apply our mathematical tool into the deep generative model? And how can we differentiate the existing deep generative model by using our mathematical ideas? So you know what? I think you already heard about the deep generative model because everybody using the ChatGPT for your homework. So like this kind of deep generative model is different from the discriminant model. Previously, we have some data, and we are going to distinguish cat picture and dog picture. That's like the discriminant model. But generative model, we are going to predict this kind of the data distribution. So this the P data, blue one, is actually our data distribution. So our model, our neural network, the red one, we are going to fit this kind of the P data distribution. So question is, can we find this kind of the red curve P model by using the neural networks? And there are several different flavors like explicit density estimation, implicit density estimation. There are many different tools like diffusion model, normalizing flow, GAN, or autoregressive, many different models. But basically, they are doing similar job like that. Can you actually make this kind of the red one by using the neural networks? So P theta is like the neural network parameter. So actually, can we make this kind of the P theta X, that kind of the neural networks by using our, some architectures. So actually recently we put a lot of energy to develop this kind of the deep generative model. But today I'm going to talk about the normalizing flow. So what is the normalizing flow? Normalizing flow is I think one of the easiest deep generative model because this is just a change of area. So actually our data distribution is very ugly. So we don't want to generate the actual sample from here. So what is our goal? So we are going to transform this ugly distribution by using some nice function and iteratively applying for the nice function. If we are lucky, then we can make from here to there very nice Gaussian distribution. Then we are luckily find this kind of Gaussian distribution by using some sequence of the function. Then we are fine. We can generate our data from here because this is well-known distribution. Then we can sampling from here, and then we can generate our sample. Then we are going to back to here, and then we can go to the actual the data set, the image, something like that, or voice and other whatever this is. So that is the basically idea of the normalized flow. But I said if we are lucky. Why if we are lucky? Because if we can find mapping here, we need to find backward mapping. So the mapping should be invertible. So if mapping is not invertible, normalizing flow doesn't work. So it's very strong restriction in the sense of this kind of deep generative model. So it developed maybe a long time ago, but not so many people use it. But after deep learning has been developed, people study this kind of normalizing flow once again, and they develop this kind of a real ambiguity first. So, okay, so they just restrict the mapping by using this kind of affine transform. So affine transform, this kind of mapping, we know this is invertible. So they use this kind of affine transform, and then they can make use of this kind of the inverse of the affine transform, then we can find this kind of mapping. So real ambiguity works very well, but still, this kind of the function restriction is too strong. So we have more freedom. We need more freedom for the high expressivity. So afterwards, they developed the invertible residual network, IResNet. So they keep the resonant architecture. So this is a resonant architecture, but they have one restriction, the richest constant of this G theta. G theta should be smaller than 1. Then, by using this kind of fixed point argument in numerics, then they can find inverse mapping numerically. So that is their restriction for the IResNet case. But that richest constant smaller than 1, that's also strong restriction. So I don't like it. So once I take a look at this kind of restriction, I thought about how can I relate this kind of strong restriction, richest constant smaller than 1. But we know some idea. Like if this is like the I-resonant class, then we know this Gx, which is constant smaller than 1. That's I-resonant. But if we think about Gx is equal to 5 times x, then that's invertible. We know that because x plus 5 times x, 6 times x, that's obviously invertible. But this is not Lipschitz constant smaller than 1. So this is not in the I-resonant class. But I want to include this kind of thing into our new I-resonant class. So then maybe our expressive power is expanded, then we can generate much better performance and much better the data thing. So how can we do that? So long time ago, we can learn this kind of, in the functional analysis, we can learn this kind of Minty surjectivity theorem. So the statement of the Minty surjectivity theorem says that scalar operator of the maximally monotone operator is one Lipschitz function. What is scalar operator? Scalar operator is just rotating operator. So we know that the scalar operator is that's invertible, and this is like the 5 times x kind of function. We can rotate it 45 degrees, then that becomes one Lipschitz function. Then we can add this one into our I-resonant class also. So by introducing this scalar operator, and this is a theorem, we are going to use it like the Minty surjectivity theorem, and then the scalar operator is one Lipschitz function. So thanks to this kind of Minty surjectivity theorem, we can say we can expand our I-resonant class by adding this kind of monotone function. We can add a monotone function, and we can also expand our I-resonant class. So for instance, this 6 times x, then scalar operator is like this, then indeed this is like the one Lipschitz function, so this is invertible. So we can add 6 times x, 7 times x, 8 times x, this kind of function into the previous I-resonant class. And this is a picture of the Professor Minty. Minty developed this Minty surjectivity theorem 1960s, and he was a professor in Yale University. And actually he didn't do anything about the neural networks, but we can pick up his idea and we can make use of it. Now we have a better idea. So like the old mathematical theorem sometimes help us to develop the new this kind of the neural networks.
So I have a question. Maybe I missed somewhere. So theoretically, we can use any invertible functions for the normalized flow.
Oh, great.
So why we focus on Lipschitz Lipschitz constants less than 1 case?
Because we need to think about the inverse.
Yeah.
It should be invertible. So we cannot find inverse as long as Lipschitz constant bigger than 1, because we are going to find inverse by using some fixed point iterative method numerically. That's the tool. How do we find this kind of the inverse?
So not an arbitrary invertible function can be used.
Yeah, that's right. Of course, we know the function is 6 times x, we can find the inverse. But that's not how we find the inverse by using the neural network.
Okay.
So we need using the fixed point iteration for the finding inverse. That's a good question. Thank you. Yeah. Anyhow, so this is a previous I-resonant class, the green one. So by adding this monotone class, then our function class expanded. So that's good news, because by adding this kind of a new function class, previously the generation is like this kind of bad generation by using the I-resonant. This is not easy one because it's like the stairway case. But this is the monotone class. It's almost fitted into this kind of the stairway case. So the FI4, it's published 2022. At the time, it was like a state-of-the-art performance at the time. Right now, we have a very fancy the diffusion model around. So right now, this is not the state-of-the-art the FI4, but at the time, it was the SOTA number. Yeah. Anyhow, it works very well. So this is like the interesting example. How do we apply mathematical idea into the degenerative model? So and it's successful, and then maybe this is not the only one. There are another idea to put into this kind of the neural network and degenerative model for the math idea. And later we can also make use of this kind of variational encoder or diffusion model. But I'm not going to explain in detail about the VAE or the diffusion model, but I'm going to explain the application for diffusion model and VAE. But these are like the similar degenerative model. Okay, and the second topic is like the AI for science. So this AI for science, I didn't make up. I didn't make up this kind of terminology. So actually, this terminology made by Microsoft. So if you go to the Microsoft, then they have like the team Microsoft Research AI for Science team, and I think he's Maxwell, and then he's a bishop, the textbook professor, and they are like the team leader of this AI for Science in Microsoft. And one of the theme of this project is like the fast neural PD solver. And of course, there are many different bio embedding and generative chemistry, these kind of the ideas. But one of the themes is like the fast neural PD solver. So that's why we are interested in this kind of the thing. But AI for science is very diverse technique. So like this is like the inverse design, one of the famous things. So what is inverse design? So previously in the material computation material, if we think about some inverse design from the data, it was very much painful. And then we need to think about the global optimization, and that global optimization takes a lot of time, and sometimes it is not working. But right now, neural network can do this kind of inverse design very well, and that is one of the major the improvement in this kind of the AI for science in this stage. So if you take a look at the material science or computational material science journal, then most of the technique they make use of this kind of the neural networks and generative model and so on. So not only this, let's go back to my problem. So at the beginning, I explained that I solved the matrix equation and Helmholtz equation by using some numerical method. That was one of one of the previous projects. So the reason why I solved this kind of the layered medium and solving the Maxwell equation, Helmholtz equation. What's the striking application? One of the applications is like a solar cell simulation. So solar cell is like a stack of the material, like many different material. And it's like the consists of the observer and emitter. So we just think about this emitter, and emitter consists of like this kind of the 1, 2, 3, 4, 5 layer, and this Bradley reflector actually consists of 4 to 7 different number of layers. So it's like many layers, and then we have to think about the materials, different materials in between the layer, and think about the interface boundary condition and everything. So that's computationally quite complicated problem. Anyhow, so our goal is to measure the reflectivity of this material. So if we have a small reflectivity number, that's good material. Because small reflectivity, then our solar cell trapped a lot of solar energy. Reflectivity is high, and that's not good for the solar cell panel. So we are going to simulate by using the numerical method for that. And well, it was successful, and I liked it. But after I simulate this kind of thing, I have a question. Because we have many layers, we measure this reflectivity by using the numerical solver. Yeah, I can calculate numerical solution by using my numerical method. But my question is, the material, kind of material, thickness of the layer and number of the layer, actually that number determined by one of the physicists. So my collaborator from the Argonne National Laboratory, he actually one of the experts of the solar panel. He taught me like, okay, using the TiO2 and SiO2 and TiO2 and SiO2, using the 10 nanometer, 5 nanometer, 10 nanometer, 5 nanometer. I didn't ask any question because he's an expert. I didn't ask any question, but actually my question is it the best material? And how about if I change the thickness of the layer, 11.5 nanometer or 12 nanometer? Then what's going to happen? But I didn't try when I compute this when I write the paper because I was busy writing the paper. So, but the other thing is I don't know how to answer that kind of question at the time. But right now we know the neural networks, we know how to do inverse design, so we may answer that kind of question. So how can we answer the question? Let's go back to the generative model. That's for the CVA, conditional variation of the encoder. It's very popular in machine learning. So if you have this kind of cute cat picture, and this is encoder, and this is decoder, and you give a condition like this is cat, and then they reconstruct cat picture. And you're going to train this neural network giving many cat picture and dog picture. And then afterward, you can just get rid of this decoder. You're going to sampling from the latent space, and then after passing through this decoder, and then give a condition like dog, and the autoencoder, the variation autoencoder, generate dog picture. And if you put a cat here, then they generate a cat picture. That's very popular technique in the machine learning and generative model, the CBA. But if we change like this is our problem. So like instead of the cat picture, I put the number of the layer and the kind of the material. The kind of material is distinguished by the refractive index, which is like the number of the vector, and also thickness of the layer. So that could be our input. And then we can train this one and reconstruct another optical device design. And this what will be the condition here? Condition could be our reflectivity. So we want to find small reflectivity of the material. So that condition is reflectivity. So once I train this model, and then when I generate optical device, I ask the VA, like I wanna generate optical device which has a small reflectivity number. So I just put the 0.1% reflectivity here, then they can generate probabilistically, they generate some optical device which has a small reflectivity. Of course, it's probabilistic model. So they may generate, they may not generate 0.1 reflectivity. They may generate 0.5 reflectivity. We don't know. But with a high probability, they can generate a small reflectivity optical device.
So in order to train the algorithm, you need a bunch of data sets, right? Is it easy to get such data? Because they have to spend lots of energy.
Exactly. So that's why I showed at the beginning, I developed my numerical solver. So my numerical solver can generate the database. So my numerical solver, I can put like I randomly generate some kind of the reflectivity and thickness of layer. I can generate 50,000 data quickly, and then probably 50,000 PDE. It doesn't take a lot because my method is very fast. Because my method is spectral element, the spectral element method. So it's specialized to fast convergence. I can generate the data set, and then 50,000 data set I can train. So that's like a combination of the numerical method and deep neural networks.
It's like a synthetic data.
Yeah, that's computational material science data. Yeah, so that's kind of popular data set. So because the physical experiments, it is a little bit different because the refractive index, the physical experiments, each paper they use different number because the physical quantity of the refractive index of the given material, it depends on their devices. So it's like the big problem about this physicist and then the physical experiments. But I don't want to dive into that kind of the physical thing. So I just want to think about the numerical case and the numerical simulation.
I have a question.
Yes.
You say you solve 5,000,
50,000.
50,000
Yes.
PDE,
Yes.
and then you use this data to train model.
Yes.
So as a result of the neural network, you get optimal design. So compare with this optimal design and the result of a solution from the PD server, does it have a big difference?
Okay. I understand your question. So after I generate this guy, I ask like the polymer reflectivity. Actually, the design give a polymer reflectivity. That was your question, right?
Yes.
Actually, it is not. That's why we have to check the sanity check. So I have a numerical solver. They generate design. I can check this one into our numerical solver. And if I ask like the 0.1 reflectivity, then they have like this kind of the reflectivity. And this is 0.1 reflectivity. Then it's like this is like the distribution which I generated by using this kind of VA. Then they have some kind of optical device, like the 1,000 optical device. Then they have a nearby the 0.1, but sometimes it's like larger than that. Very smallly, they have smaller than this kind of 0.1 reflectivity. So in this case, we need an active learning. If we generate like nearby 0.1 reflectivity, then we can just take it out, and then we can relabel this kind of data set. we can do the data augmentation. And then retrain it. It's like we can do the 2 or 3 times this kind of iteration. Then the variation of the encoder is specialized generating small reflectivity optical device design. So that's like the sort of the active learning. It's very beginning of the active learning. I didn't need any major optimization though, but it worked like this. So the two of them is like the previous research, like the 2019, 2021, developed by the engineering, like some mechanical engineering, electrical engineering, they did it, but they 1.8%, but we did like 1.5% by using the deep learning method. And notably, maybe the first one, maybe second one, they use the global optimization. It takes like 2 or 3 days, but my method is like 2 hours, then I can finish our simulation. So that's very efficient also. And we can expand this idea into this kind of the actual material science problem. So it's like the 3D printing unicell. So this is the unicell, it's like image. And then if you can just you can input this kind of the unicell, then they can the 3D printer generate period material, and they generate this kind of period material, and then they can have some kind of their specific mechanical property like Poisson ratio. So this is like we can generate this kind of database by solving the linear elasticity equation, and we can generate maybe 25,000 and 50,000 something the data set, and then we can actually play the game. Then our VA can generate our negative Poisson ratio, which is what we want, like the generating negative Poisson ratio at a material. So this is also one of the expanding the extension of our research. And then also we can apply this onto not only for the VA, diffusion model can do it, in fact. So like the diffusion model on the left-hand side, if you go to the noising and denoising process, and you can iteratively this noising and denoising many times, then they can generate very clean and nice picture. That's what the diffusion model is doing. So we do play the same game by using this kind of the unicell for the 3D printer, like the noising and denoising process over and over again. And we can find this kind of the clean and nice unicell image. And then we can give a conditioning and check the guidance, then the generation is getting much better by using this diffusion model. And then later we can put this kind of the 3D graph structure, and then we can do this kind of the nice results, and it worked. This is like the actual device by using the 3D printer, and then it's physical experiments. And our generative design actually works for this kind of physical experiments. So it matching very well. Red dot and the solid line, they are matching together very well. So that's one of the application. But I'm not going to explain in detail about this kind of material because a little bit different from what I want to say. So anyhow, another thing is like this kind of geophysics. So geophysics is, I showed the picture of my previous research of the geophysics. Right now, the geophysicists, they using this kind of the deep neural network a lot. So one of the application for the geophysics is they have a satellite data. The satellite data is like a low resolution, but by using the generative model, they can do the super resolution, and then they can do the high resolution image. Then they can have a high resolution data, and our numerical simulation, our initial condition, our boundary condition, it's much more accurate. So our simulations get better and better. That's one of the direction of this kind of the geophysics research by using the generative model. Okay, so I mentioned many blue sky and positive things about the neural networks, but there is also a drawback of the machine learning and deep learning, because machine learning is not always robust and reliable. That's why we have to analyze this kind of machine learning and deep learning in some sense. This is one of the examples why machine learning and deep learning is not robust. So it's very famous example, the adversarial attack. So this is a picture, and we can ask this one to the neural networks. The neural network says, hey, this is 91% peak picture. we are happy. But if we introduce this is noise times 0.3, 10 to negative 3, 5 times 10 to negative 3, then in human eyes, this kind of noise, we cannot see them. So actually, we can add this onto this picture, and this is the result. Okay, and this picture, we cannot see any difference this and this between two, right? In human eyes. But we ask neural network, what is that? The neural network says this is 99% alignment. So we can fool the neural network by introducing this kind of very small noise. So that is called adversarial attack, and that this is adversarial example. So why this is big problem? That's big problem for the safety of AI. So there is a stop sign, and imagine that you're having a self-driving car. And self-driving car just moving, and they take a picture, stop sign, they have to stop. But there's some kind of the bad pattern, dust or sticker, and whatever this is. And then our neural networks distinguish this much L sign, and car doesn't stop it, they just keep moving. And that could be a big accident, right? So this is like a very serious issue for that. So how can we analyze that? So when I see this kind of example, I sort of like, okay, so look at this. This is initial condition, and this is perturbation. So it looks like numerical stability and instability of the perturbation of the initial condition to me, because I'm educated by the numerical analysis. So that's quite similar problem. So let's think about the neural ODE. So the neural ODE, what's the neural ODE? So this is a discrete resonant architecture, and neural ODE, take this one as something like the continuous ODE, like the function. So this is like a continuous function like the ODE. So this is called the neural ODE. So if we think about the resonant as a neural ODE, then that kind of adversarial attack is like the initial condition perturbation. So I take this, and then using some special numerical method, which can prevent error doesn't propagate by using this kind of the strong stability TBD numerical method, then we can prevent that kind of the adversarial example, give a misclassification, just a little bit, not important, because that's very hard problem. So anyhow, we introduce this kind of new architecture, stem from the numerical PD idea, and then we can have some kind of the, better performance at the time. But this problem is very complicated. So this is still widely open because if I say something, okay, so like some cipher 10 data set, like if our SOTA number is like the 95%, for instance, the adversarial attack is like the 40% accuracy. But if we using this kind of thing, it's still 45% accuracy. So still there are big gap between clean data and adversarial attack. So there are many things have been done. So it is still widely open problem. So, and it's I think it's very popular in 2020, 2021. And at some point, not so many people just give up. And then 2023 and 2024, people start to working on this kind of adversarial attack once again. It's like the trend is go back and forth. So, this is still good topic, I think. Okay, so the last one is like mathematics and machine learning working together. I think this is most interesting parts for you guys, like the PD and machine learning and numerics all together. So let me start with this kind of interesting two papers, like computer assisted proof. So this paper written by the Triangle Master, and these people are very famous fluid guy, and actually they insist that they find we know the 3D Euler equation is very famous, and they find below profile self-similar is 3D Euler equation by using the neural networks. So they published this paper in the PRL, and yeah, I don't know. Mathematicians still doesn't buy this one. Maybe they buy this one. I'm not sure. But the result is very interesting to me. And the second one is written by Tong Hao, and then he also working x-isometric 3D Euler equation, and also he find the flow profile by using the neural networks. And well, this is for something like computer-assisted proof. So this is one of the new territory of the research, but it's very beginning of the this kind of the computer assisted proof. So I'm not sure this is active or not in the future, but I just want to introduce you guys. Okay, anyhow, I want to speak about this kind of scientific machine learning. The scientific machine learning is very popular in these days. So DOE and DOD, they put a lot of money about this kind of scientific machine learning these days. So that's why many people are working on this kind of scientific machine learning right now. So this is one of the popular scientific machine learning architecture, PIN, physics simple neural networks. The architecture is very simple. You have an input, coordinates, output, solution, and then how can we train the neural networks? The solution, left-hand side minus right-hand side of the work, and left-hand side minus right-hand side for the initial boundary condition. And we are going to reduce this residual loss, and then we can train our neural network to this loss goes to zero. And that is it. That's the whole part of the neural network. Very simple. But this is not perfect because it's not very efficient in the sense of the computational science. So later, people working on this kind of the operator networks. Operator networks, they have this kind of the mapping. So they try to learn the mapping from the input to the output. So input could be a coefficient, source term, initial condition, boundary condition, whatever this is. And they are going to learn the mapping to the solution. So learn this mapping, they need some kind of, to learn this kind of mapping, they need some kind of database. So they need to generate the database, and then they can train this kind of mapping, then they have a very fast inference. So it's computational science that's very efficient in some sense. And this is one part of the operating networks, and then they insist that their baseline, even though their baseline is very high resolution data set, their neural network prediction, they can use maybe 16 points, like the coarse data points, as coarse collocation points. They can, generate very nice numerical, they predict very nice numerical solution. That's what they say for the, computation efficiency. Okay, let me skip this. So I explained physics for neural networks and operator learning, and they were some pros and cons together. With PIN, it's very easy to implement. You don't need to know anything about the PDE theory. You don't need to know anything about the FEM, FVM for the PIN. And they can be applicable to various domain equations. And this is unsupervised learning, so you don't need any database. That's two parts. But bad parts, it's not actually it's not a PDE solver. It's regressive. So once you have some fixed initial condition, fixed boundary condition, fixed source term, then you train your solution that, and then if you change initial condition once and boundary condition whatever, then you have to retrain this again. So that's not efficient in the sense of generating database something. And make boundary condition another issue for the PIN. Operator learning, it's efficient because they can do multiple instances. That means their input could be an initial condition. Input could be a forcing term. So once they train your network, their inference, their prediction to the solution, that is very fast. So they are very flexible from the initial boundary condition and whatever this is. And then they can use some computer vision architecture. And that part is supervised learning. So you need to find input output data set, pre-computed input output data set. For this, you have to go back to the numerical solver. And then you have to generate the numerical solution. So it's not efficient in some sense when you train, and then you can think about the supervised learning. But after training this one, it's very fast and easy to predict multiple instances. But accuracy is not that high, and generalization errors could be high, and boundary condition is also wrong. So this is like the pros and cons for this kind of scientific machine learning problem. But these are like the limitation. So accuracy is not that high. Numerical solver, if you have a more fine discretization, error going down and down, we have belief, and then we have a complete theory for the FEM, FDM, FVM. So it's reliable. And that's kind of the good part of the numerical solver, but this is not the lower accuracy. And the training time is this kind of limitation. So why do we have to do that? Very bad points or rates. But for the advantage for that is like they can overcome the curse of dimensionality. and they can do the fast inference, and they can do very well for the inverse problem, and then they have some kind of potential to tackle these kind of complex problems, multi-physics problem, and so on and so forth. So let me give an example. One by one. How can we handle this kind of scientific machine learning in our actual PD problem? So this is like the BGK Boltzmann equation. I think this is like the center of the BGK Boltzmann equation in Asia, I guess, maybe in the world. So the computation in the center of the numerical computation, that's very nasty. We really hate it because this is integral differential equation. So we have integral, and this is if we think about the BGK equation, even though BGK equation, they have a rho T and rho UT is like this kind of the integral. It's very nasty for the numerical computation, first of all. Secondly, the dimension, the full BGK equation, time, 1 dimension, x, 3 dimension, v, velocity, 3 dimension. So it's total like 7 dimension problem. So volumetric method, that's very, very hard to solve it. So without like some kind of parallelization, it's not easy to solve it. So that's not, popular, and that's not good for the numerical analysis. Of course, there are some, leading to, make a simulation, this kind of thing, but, they need some kind of a parallel computation, massive computation. But we can just get around this kind of thing by using our neural network method. So this is 7 dimensions. So volumetric method for the 7 dimensions. So let me put it this way. So in x direction, I just put the 20 collocation points. So x, y, z, then 20 to the 3. And for the velocity, v1, v2, v3, we have 20 collocation points, then 20 to the 6. And time, discretization, 100. So it's like a very, very large number of the discretization. So we don't want to handle it volumetrically. But in the sense of the neural networks, everything is like sampling basis. So we can do sampling. So it's independent of the dimensionality. So that's why we can overcome the first of the dimensionality. And if we introduce like a better architecture, like some kind of like S-spin structure, which I developed, S-spin structure, then we can do some kind of a tensor decomposition, and this tensor decomposition make it fast, everything. So this is like comparing our S-spin architecture, and this is numerical PD method. So this 1D means like 1 plus 3D. So 1 plus 3D is 240 seconds, and 1 plus 3D, and 2 plus 3D, 300 seconds, 2 plus 3D, 300 seconds, 3 plus 3D, 3000 seconds for our S-spin architecture. And this is a numerical solution by using the S-spin architecture. But numerical PD, like 2 plus 3D, it's already, a lot of time. And 3D plus 3D, it's the single GPU. By using the single GPU, it's not applicable. So, our S-spin architecture is much fast inference. Of course, there is a price to pay. Maybe it is not for the accuracy. Maybe NPD, if you have many discretization, maybe it takes a lot of time. Many discretization, then we can get a better solution. But S-spin architecture, that doesn't, matching with the number of discretization and the error discretization thing. And also the inverse problem, this is an example of the inverse problem. So this kind of neural network is very good at design for this kind of finding inverse problems. So this is the Helmholtz equation. So this is the wave number. We can find them very quickly, the wave number. The red one is our pixel, our neural network architecture, and this one is like the general K, but we can find very quickly, very small number of iterations, we can find this kind of inverse problem. And also, they put 3D Navier-Stokes, but actually this is 2D Navier-Stokes. 1D, it's like 2 plus 1D. So in fact, this is the 2D Navier-Stokes equation. Anyhow, this is like the lambda 1, lambda 2 is like the coefficient in front of the Laplacian term, the second derivative term. They can find this kind of our pixel, the blue one, the red one, our pixel very quickly find this kind of the coefficient by solving the inverse problem. Because the neural network finding forward and finding inverse for the neural network, that doesn't different. That doesn't give any difference between them. Okay. Okay, so and another thing is like for the fast inference. For the fast inference, so we developed the neural network architecture. We call this is FAIONet, which is based on the finite element method, and then we can have some kind of the test between FEM. That means we have some kind of Phoenix, the package, like the famous package for the FEM. So we can compare computation time FEM versus our FAIONet. If we generate like the 10,000 solution, the Phoenix takes like 100 seconds, but our FAIONet, the neural net architecture only takes 29 seconds. So in the sense of the inference time, the operator learning is much faster. So in terms of the inference time, the operator learning is much faster than classical FEM method. And we can do this kind of thing by using this is Gromov-Stefanski and Navier-Stokes equations. We can do many different simulations by using the neural network architecture and operator learning architecture. And also many different geometry we can handle it. So like this is dolphin domain, it's like a very fun domain. And then we can actually handle this kind of the dolphin domain together. And okay, let me skip this one. Yeah. And so in fact, let me say this one. As I mentioned, this is like the new neural network architecture developed by my group, my team. And actually that is called the FAIONet, the finite element based neural network. So this one is actually based on the finite element method. So that means we can do some analysis, error analysis. Normally physics informed neural networks, this kind of thing, it's not easy to do the error analysis, but we can do some error analysis for that because we are based on the FEM. So this is like the error, kind of the error, approximation error and generalization error, optimization error. So please note that we just assume that optimization error is more enough. Okay, so we don't care about optimization error, but we do care about the generalization error and approximation error. And then we can do some analysis here. Like in FEM theory, we can do P1 element, P2 element, we have this kind of error analysis. But in our FAIONet architecture, we can do this kind of the error analysis. So we have the H is the number of the discretization, N and M are number of the neurons and number of the sample points. Then we can do this kind of the error analysis that's available because generalization error and approximation error can be done. And in fact, this is not easy to see in the neural networks. Normally in numerics, we can find this kind of the convergence, the log plot, because we have a P1 and P2 element. This kind of the convergence plot is normally seen. We can normally find this kind of convergence plot. But neural networks, it's not easy to see that, but our architecture is based on the finite element method, so we can do this kind of convergence plot. So it's getting much more closer and closer to numerical solver. And analysis is getting, I can say a little available because we say optimization error assumed to be small. But optimization error can be done by using the neural target plan or other techniques. So this is the analysis part. So let me skip it because I have only 5 minutes. So the last one is like at the beginning, my very first slide, I mentioned that I do some singular perturbation and boundary layers. It is very important topic in fluid dynamics, a very complicated one, because they have this kind of very sharp transition nearby the boundary. So that's why we produce this boundary layer. And this sharp transition cannot be captured by some classical technique. Classical numerics also cannot capture this kind of thing. Also, neural networks, it's really hard to capture this kind of thing because of the spectral bias. That means neural network trying to learn low frequency first, and then they think low frequency is done, they move to the high frequency. That is called the spectral bias. But we have a sharp transition that is like sort of high frequency. So neural network cannot capture this kind of the peak of this kind of the points. So how can we handle that? So we introduce this one by using our semi-analytic method. So can I? So thermal method. So this is a usual pin architecture. Like we have a hard constraint for the boundary condition, and this is neural network, and this is pin architecture. And pin doesn't work for the boundary layer and singular perturbation. But if we introduce like this kind of some change of the scheme, this is like some additional term, and this is like the e to the minus x over epsilon, that's the profile of the boundary layer. Then if we have this kind of the modified pin architecture, then we can capture the boundary layer like this. So this is very sharp transition, but we can capture it by using the physics simple neural networks. So, but the question is, how can you find this guy, e to the minus x over epsilon? This is not free. That came from boundary layer analysis and singular perturbation analysis. And that can be developed by some mathematical analysis and PD theory. And we can pick up this kind of this one is called corrector function. We can pick up this corrector function, and we can make use of a corrector function, and we can, fit this kind of the nice prediction. And this video says like, no boundary layer, we can find the accurate solution. With the boundary layer, sharp transition. So normal neural network cannot capture this kind of sharp transition. But our method, epsilon tend to negative 5, this epsilon in front of the second derivative, then they try to capture it and they can fit it like after 10 epochs because of this kind of the corrector function from the mathematical analysis. Okay, let me see. So closing remarks. So this question I already asked from my students and some of my postdocs and some of my friends. So should I learn machine learning, deep learning for my future research? And how long they will survive? I don't know. I cannot say, but I can say there are a lot of interesting problems to be done. Actually, I introduced many things today, but this is like the partial improvement, I would say. There is no complete analysis and there is no complete improvement. Some are still widely open. So I would say there are a lot of interesting problems. So maybe you can give us some of the contribution if you dive into the machine learning and deep learning, or you can dive into the computer assist proof, which I showed you in the beginning of the third part, the part 3. Then you can do some nice improvement for that and contribution. Okay, and to close my lecture, I'm going to say some of my future direction. So I want to actually make use of the scientific machine learning for this kind of complex problems. So like this is like the numerical weather prediction thing, and this is like the GCM, the global, the climate model, GCM. So GCM, their domain is very large, like the whole of the Earth. The computational cost is very, very high. So maybe we can train this one in the beginning, then maybe we can do the very fast prediction. Our numerical weather prediction give a much more ensembles, then they can do better. They can do some kind of uncertainty quantification better than now, and they can do some of the accurate prediction for the weather. And secondly, this one is like the actual impact of this is like the multi-physics one. This is a very complicated problem for the battery simulation. So actually, I'm working on one of the battery simulation with the Hyundai Motors. The equation, the battery simulation PDE, it's like the 12 coupled PDE equations. It's very, very painful, but neural network can predict by using this kind of 12 coupled PDE. So that's for the complex system. And also, this is one of the interesting examples. This is like the ice sheet melting problem. So this is an ice storm. So it's very big problem for the Alaska. Ice is melting and freezing again, melting, freezing again. That gives us a lot of like the cost for this kind of global warming and other kind of issue and environmental thing. So the Department of Energy and DOE and DOD, they put a lot of money and then they make some kind of a new grant for that, like this kind of the ice sheet melting and freezing kind of thing. And this is the PDE for this kind of the ice sheet melting problem. So it looks easy, like H time derivative grad dot Q minus A0. Well, that looks easy. What is Q? Q is integral of U. Okay, what is U? U is integral of A times gradient H p to the 2, something blah blah. And what is Q? And Q is like this way. And that means like, you have to do many complicated like the numerical simulation. And this is also inequality. So it's not good for the classical numerical PD method. But we can optimize this one by using machine learning. So maybe we can handle this kind of complicated PD problem. And that model actually developed by my former advisor in 2023 something. And then I want to make some simulation for this kind of complicated PD problem because classical numerical PD cannot do it. That's why we have to work on this kind of scientific machine learning problem. That's a value of it. That's what it is. And now that's the end of my slide, and thank you.
Any questions?
This may be off the topic, but what do you think about reinforcement learning approach to solving PDEs? The PINN is a supervised learning approach, and I saw that the operator learning is the unsupervised learning approach. So,
PIN is unsupervised, operator learning is supervised.
sorry. So, is there any approach from reinforcement learning areas?
Yes, yes.
And
There is many approach for the RL. So one of the famous one is it's a little bit blue sky, I guess, because it's very complicated problem. So think about the multi-domain compressible Euler equation. Then you may imagine the shock inside the domain. Shock is moving. You don't know where shock happening. Your shock occurs, right? So the RL guys, they try to find the position of the shock by using the RL. And then they know where is the position of the shock. And then they can do some kind of the mesh discretization, adaptive mesh refinement thing. And then they can find, better numerical solution. That is one of the applications for the RL. And the other one is RL is like, they can do some optimal control problem by using PD. So that's another, maybe another big direction. So I'm not going to talk about it, but RL also one of the main parts. And in fact, I actually at the beginning I mentioned about some kind of robot advisor. This guy, the robot advisor, the AI training thing, I use PPO. Because our episode, the reward function is very clear. If we earn money, then this reward, if we lose money, that's negative. And then our episode is one of the time frame, but we need a tip data in this case. Like tip data means we need like a very short time frame, and then we need like some kind of the stock data set, and then we need some kind of analyzing by using the PPO method. And that worked very well. So RL is one of the main direction for this kind of deep learning, but maybe Youngjoon doesn't buy it. yeah, Youngjoon, he mentioned that RL is not so good, but I still think RL is one of the good direction. That's what I think.
thank you so much for the detailed answer.
Any other questions?
My question might be too specific, but you mentioned about deep net network, I guess. Is it still widely studied, or is it like off the attention? I'm just interested. Is it deep net network widely studied recently, or is there any alternative for deep net?
His record is right.
Maybe we can talk later.
Yeah, I would say, yeah, there are a little fighting between DeepNet and FNO, between them. So DeepNet guys write a paper, like DeepNet is better than FNO. And later, FNO write a paper, FNO better than DeepNet. But I would say, in terms of the accuracy, FNO is better. And but in terms of some kind of domain, flexibility, DeepNet is better. But I read a paper last year, like the GeoFNO, that they also overcome this kind of a domain issue. And FNO is like the full rate feature. if you think about the boundary condition is not periodic, maybe you have a Robin boundary condition, some complicated boundary condition, maybe you have to think about another way to think about this kind of FN architecture. So FN and DBONet, they are fighting each other, and if you want to write a paper for DBONet, then maybe you can submit your paper DBONet friendly journal. And there is an FN friendly journal, maybe you can find it. And my method is not DBONet FN, no. My method is like the new method. It's unsupervised operating networks. DBONet FNO is supervised learning. My method is unsupervised learning. So my method is like kind of a little bit different way. So we are not competing with DBONet FN. We are lucky, but they are fighting always.
So are they still fighting, or is it over?
So last year, I submit the paper to iClear, and I compare only with the DBONet. And the reviewer says that, why didn't you compare FNO methods? So, and I think DBONet is still alive because, DBONet, the Karnya Dawkins, and these are like the big group still advocating. But, operator learning is not, limited to DBONet and FNO. There are many different operator learning methods out there. It's combined to the computer vision. So neural field, the neural field guys also pick up this kind of the computer vision guys pick up this kind of the operator learning terminology, and they can combine them together. So I would say if you want to study DBONet, it's not too late. Maybe it's never too late.
Any further questions?
Can I see the slide with the wing feature, wing cross section?
This one?
Yeah. What can you explain the meaning of sharp transition inside boundary layer? What does that mean?
Okay. So forget about this picture. I didn't actually explain you what's the singular perturbation boundary layer. So the definition of the singular perturbation means that if you have a highest order, and you have a small primary epsilon in front of the highest order derivative, then that calls the singular perturbation problem. And you have a boundary condition like this. Then this is you can think about the boundary layer issue. So if epsilon is like not too small, then your solution profile is like this. But epsilon getting smaller, then your solution profile, you can solve this ODE. The solution profile is getting like this. And epsilon is extremely small, like this. And you can see the very sharp transition near the boundary. You call this one is boundary layer. Okay, and same thing. This is very easy problem. You can see the same thing happens to this kind of the wing star, because when you think about the fluid, what kind of equation do you think about? Navier-Stokes. So means Navier-Stokes and viscosity, right? And then viscosity is very small, like this kind of the air, right? And the small viscosity, and then you can think about the incompressible Navier-Stokes. You can think about the nu, the viscosity goes to 0. That could be an incompressible Euler equation. And there is a you can give a boundary condition for the Navier-Stokes for the maybe homogeneous Dirichlet boundary condition. What about the boundary condition for the incompressible Euler equation? You can think about the impermeable boundary condition. Then there is a discrepancy of the boundaries, limit problem and actual problem. So they can produce this kind of the boundary layer between them. So that kind of thin layer actually came from this kind of mathematical equations.
So boundary layer is not physical layer of the
It's
wing.
physical. It's physical. Yeah. Technology of boundary layer developed by the Handel in 1904. He's a physicist and engineer, and he observed this kind of the Handel boundary layer issue at the beginning. And you can see the boundary layer, many of this, wing star and other kind of the many fluid problems. It's very much physical.
But why inside the boundary layer? I mean, inside the ring,
Yes.
there's no fluid.
Not inside. This is solid.
Yeah.
This
so-
is solid and this is fluid.
And
So-
why inside the boundary layer?
Boundary layer is very thin layer. Okay. No one your question. So boundary layer means very sharp transition. Okay. That is boundary layer. And that is outside boundary layer. And this is again boundary layer. So that's why we call it this inside the boundary layer, we can see the sharp transition.
Any more questions? Okay, now let's take a speaker.
Thank you.